What functional is best? Well, there are, again, the two criteria. Practical, for whatever you're interested in, and the other one is it actually works. Sufficiently accurate depends on what you want to calculate. So let's go to that for a second. Okay, I'm going to talk about two quantities. I'm going to talk about two kinds of data, and then I'll talk about NMR in the end. The first kind of data is structural. There are very, very good experimental data for a couple of thousand small molecules. There are, on the other hand, something like 1 million crystal structures. So crystallography is the dominant structure tool, and the accuracy there is an order of magnitude less than gas phase microwave. So my basic feeling is that if one wants to really compare to experiment, it really should be the crystallography standard as opposed to the gas phase standard. It doesn't say you can't match it, but I think if you really want to talk about how good am I, it's really more realistic to use the crystallography standard. It turns out that theories get structure rather well. And this is actually using gas phase data on 50 or 60 small molecules. I have two theories here. Is B3LYP experiment versus calculation, a large basis set. And they're not perfect, but they're scattered by the line. Omega looks actually worse, but it's better because it's got a systematic error to it. But you can see that structure is pretty good. This is a range of 0.3 angstroms or something. And if you look at different functionals of the set I've given, I think I've eliminated the double hybrid one here. They're all pretty much the same as far as looking at this large data set, and they're not very different as far as what. So structure is inherently something relatively simple to get right. Oh, I'm just talking about bond lengths because I'm lazy. But it's very, as soon as you go past, in structure, as soon as you go past trying to measure distances, it really becomes really impossible to tabulate. Yeah, basically this comparison is carbon, nitrogen, carbon, oxygen in simple molecules. And this is using gas phase standards, and so our accuracy is fine. So X-ray crystallography is the reference. Now, the other point I want to make is that once you have established a functional as acceptable with a large basis set, something that's rather expensive, what happens when you try to go to something smaller? And here is this very large base set on one axis, no experiment now, somewhat smaller basis set on another axis, and they're perfect. And here is a very small base set on the other axis, and they're pretty close to perfect. So what it's saying is that structure is a relatively easy problem, a relatively easy quantity to get right. Now that's important because getting structure is a first step in an investigation, what something look like, and it's also a major cost step. If you have something with 100 different geometrical variables, to actually find out what it looks like is not so trivial. I won't go into this because I don't want to run out of time. But what I've been talking about organic molecules, the theories have no restrictions on what they can really go after. And in recent years, organometallic systems have been commonly examined. And you can see here that these are errors in metal carbon bond lengths. These are carbines and carbines. They're a little bit larger. But again, you can see that there isn't much difference between the different methodologies, best and worst. But to give one example of an organometallic compound, this is a famous one actually. This molecule with two nitrosyl groups. One of them it's a dimer. One of them is linear and the other one is bent. And you can see the theory is actually reproducing that structure. It's a famous structure rather well. It's getting the linear one as short bond length and linear, and it's getting the bent one as bent and a longer bond length. This is a metal nitrogen bond length. When you come to energies, the situation's quite different. There are databases of energy data, heats of formation, for about 2,000 molecules. The ones that have only oxygen and carbon are pretty good, a couple of kilocalories in heats of formation. The ones that have other elements are much less reliable. And the reason is very simple. The experiments are combustion experiments. And when you burn something with carbon and oxygen, you get carbon dioxide and water, obviously. When you burn something with sulfur in it or with nitrogen in it, it's not quite clear what you get. And so a lot of the problems on combustion is what are the products. The other technical problem with combustion is that if you're an organic chemist and you spent 6 months making a compound, the last thing you want to do is burn it. And so the experiments are really not very common anymore. It's turned out that probably the best source of data on the stabilities of small molecules is from theory. And as I mentioned earlier in the development of density functional theories, there's been quite a bit of effort now put in making real databases of energetics quantities for organic molecules primarily. It turns out that energy calculations are much harder than geometry calculations, and it takes fairly good functionals with reasonable base sets to actually get things right. Now, there's a lesson here, and the lesson is that one has learned that if you make one never looks at an energy of a molecule, one always looks at a reaction energy. If you make your reactions subtle, then you're likely to do much better than if you make them not subtle. I think my example here is the following. If I take something completely unsubtle, breaking a bond, it turns out this is rather hard to get right. And taking phenol and breaking it into phenyl radical and hydroxy radical, it's hard to get right. And if you take a plot of good functionals and you simply plot, 20 or 30 bond dissociation energies, you can see that the errors are sizable. Look at maximum. And you can also see there's a significant difference between the functionals. B3-lip, the most popular functional, is significantly worse than all the other ones. Even so, there are big errors associated here. Still 9 or 10, this is kilojoules errors. If you make your comparisons more subtle, then you do better, but you still see variation. Here's an example. Let's look at the energies of different isomers. And so C3H6O has a bunch of different isomers. If I just look at that kind of comparison generally, saying here's a molecule, here is all its possible isomers, and you get a lot of them. That is more subtle in the sense that I'm at least maintaining the number of bonds or electron pairs. I'm not breaking any bonds. How well do you do there? Well, again, I can summarize that in a strange plot. Here is 30 or 40 compounds. The red line is experiment. The green dots are from good calculations, and in general, the green dots are excellent. Sometimes they're far off, which probably means the experiments are wrong. And the vertical lines are the range of density functional theories. So if I take the 8 theories I've been using and I just look at what they are, you can see, in fact, that their theories are actually giving different results. What this is telling you is that you really, before applying a method, have to have confidence or knowledge, at least, in what its performance is. This is taking the same plot, it's taking 2 models out of the plot and looking at how far they vary from, in this case, the green dots. And you can see that B3-lip, which is the most commonly used method, is pretty sloppy, whereas you go to a more modern method, you're pretty good. This is saying you have to build up confidence in what you're doing. I'm going to skip this. This is about tautomers. And I'm going to skip this too.